Hey everybody, welcome to my next video. And in this one I'm finally starting the HAL real tutorials. I only talked about HAL and how to use it and how to navigate this environment, but now we're gonna go to the first video as I did it with the standard peripheral library, which is the GPIO. So this is the simplest but yet the most important one because it connects your processor to the external world, and it can also light up LEDs, which is also awesome. So if you're new to my channel and you don't know, I always recommend this discovery board. It has plenty of peripherals on board, it has a plenty powerful processor, and it's very good to learn and to also prototype with it later because it doesn't have a lot of pins already populated by some ICs or pull-up resistors and stuff like that. So I really like it and I use it for debugging all the time. So this is this out of the way. So as in my fashion, I'm just gonna introduce you to the GPIO peripheral a little bit. So I have a few things opened over here. So let's just start with this one. Let's go into the datasheet and just randomly it's open on this one. Let's go to the chapter 3. This is the datasheet for this family of processor. And if you go into the pin notes and pin description chapter, you can see all the footprints, so the physical dimensions and variations of this processor are here. So this series is starting with an 64 pin and it goes to the massive, I think it's 176 pin LQFP and also 176 BGA one. And the most important thing is to know which one you're getting. It's determined by what pins you need, what peripherals, or what sheer number of GPIO pins you need. So this is the first thing, is you have to find out which kind of processor you need and also what kind of space you have on your project. Then you're gonna simultaneously use this part of this datasheet. So the first thing is, this is the table for the definitions. This is very important. We have your usual declarations of the pin type, but basically most important are these two. If the pin is 5V tolerant or not. So if you're using some kind of peripherals outside that are 5V, but your processor runs at 3.3V, as these do, then you're gonna need a pin that is 5V tolerant so it can withstand an input. Project I did required a 5V input that should be lowered to ground, so I was using the GPIO portion for the pin that needs to be 5V tolerant, and I'll show you later what happens if you do it on a pin that is not. So these are the way, this is the tables. It starts with the pins over here, and here there's the pin name. The name always starts with the pin, so this is the port, and A, B, C, D, E, depending on how big the processor is and how many GPIO cells it has different ports, and each port is just a bunch of pins. So in this case, each pin or each port commands 16 pins. So you have 16 pins on A, B, C, D, E. I don't know if all are populated, but this is how it usually goes. And each pin also corresponds to a physical pin on each package. And different packages have different number of pins from 64 to 176 and different names. So in the BGA they are usually marked in like a grid array in groups, so it's like A, B, C, D and so on. And in normal pins they are just from left to right. So if you go over here, here's the number one, here should be the mark for the number one pin, it's here, and goes around like this. So this is how the pins are labeled. Also the name pin, which is gonna use in the code, so this is the name of the pin in the software world, and this is the name of the pin in the hardware world, and this is the name of the pin from the peripheral standpoint and for our needs. So this is what the pin is actually used for, apart from just being high, low, or the input. So this is just the basic. It can also connect the outer world to the peripherals of the inside of the microcontroller. So different, in this case, let's just go to a pin, timer output, and I don't know what the hell this is, and ADC 3. So this case, this process have 3 ADCs inside, and this one is connected to ADC input 7. Let's find an, oh, here it is. Here's a one pin that's connected to all 3 ADCs input 10. It's also for USB OTG functionality. It's for USART, Ethernet, timer outputs, Let's find something else. SPI is I squared S somewhere, probably I squared C and stuff like that. So this is gonna help you determine which pin you need. Also, multiple pins are connected to same peripheral. So in this case, this pin is connected to ADC 1 and 2, so you can use either one of those. And maybe multiple pins are connected to the same part of the peripheral. So if you need a pin that is physically unable to be different place, so if you need this pin over here because the peripheral is here, so you cannot use this one, you can search what this pin can capable of, so if it does meet your need. So this pin, is it connected to the peripheral of your need? So this is the one table that's gonna spend when you're designing your circuit, so you're gonna have to have used to this. Also, which pin is connected to the certain peripheral on the bottom, and this is everything that you're gonna need while designing the circuit. This is pretty much it. So let's go to the next document that you always should have, which is the reference manual. Oh, let's go to the beginning. So this is the Bible for everything that this processor can do and how does it do it. It's quite long, but depending on your processor, it's different lengths. So let's just jump into the GPIO portion. So this is gonna talk a little bit about the workings of the GPIO and how to control it and everything. So this is up to 16. So this is what I told you before, 16 pins or IOs for each GPIO block. It has different configurations that I'm gonna talk about with this lovely diagram over here. So this is the construction of the GPIO peripheral portion for each pin. So you can multiply this for 176 pins. Here the so this rectangle is the physical designator for the physical pin. So this is the pin that comes from the package into the processor. The first thing is the protection diode. If it's 5V tolerant pin, this diode will be able to go to the 5V rail, or if it doesn't have one, it's gonna be a large enough voltage drop across this diode, so it's gonna only turn on if this signal is larger than 5V. This is important because you have only a 3.3V input pin, as I did when I was doing something and I made this mistake. This diode were connected to the VDD, so the 3.3V. So if the input was above the 3.3V plus the voltage drop of this diode, usually 0.7V. So if the input voltage is 5V, which is greater than 3.3 plus 0.7, which is 4V, this diode is gonna conduct to the 3.3V, and if this voltage is large enough, you can damage this diode permanently, and diodes do fail short. So this pin would be shorted to supply forever. So this is one way you can destroy the pins. Also for this diode, which is for the negative voltages in this case, lower than ground, in this case VSS, which is going to be internally connected to ground. Here we can see the pull-up and pull-down resistors, very useful, although if you have some kind of buttons, which we're going to talk about later, it's always good practice to introduce external resistors for prototyping, measuring and stuff like that. But if you don't have space, and if the boss really doesn't like you and it's really counting every penny, you have internal pull-up and pull-down resistors. You have full control of this. And this is the smart part of the input. So this is the input part and this is the output part. You can see all the fancy stuff like here. Let's just concentrate on this part. This is a very traditional thing you're gonna see in the electronics. This is called the CMOS pair, or the complementary output driver pair, totem pole or anything like that. It's comprised of the NMOS and the PMOS semiconductor transistors. So this is gonna be connected to the supply, in this case 3V, and this is gonna connect the pin to the ground. So this is gonna have this hard driving mode, push, pull, or push the voltage out or pull it down. So this is why it's called the push-put output type. It can also do the open drain, as you can see over here. This means that this transistor is turned off, and this one can, if it's off, it's off. If it's on, it's connecting this point to the ground. So when it's off, it just opened. And why it's called that opened or disabled in this case, so the both one are disabled. That means that this pin is disabled or is in state of tri-state, it's sometimes called, or the high impedance, and this is because these transistors are open. But well, you might ask, well, there's gonna be some kind of resistance. Yes, but it's very, very high. I have this little snippet from our lecture books. So this is a diagram of the workings of a metal oxide semiconductor or a MOSFET. Field effect, I forgot that. So this is a N-type. You can recognize it because it has current flowing into the drain and out of the source, and this semiconductor N-doped semiconductor parts, in this case, that are connected to the connection points, are N-type, and the substrate is P-type. So because this is N-type, so the majority of the current carriers are electrons. So these conduct very good this conduct current very good, and this channel that's gonna be induced in here by the voltage applied to the gate is gonna create a channel of electrons, and it's gonna create a current flow. So electrons are gonna go whip over here. So it's the other way than the current we designed it to flow. So if no voltage is applied, no channel is created, and these points are quite far apart. This is the width of the channel, and because they're not electrically connected, and this is P-type, and because this is P and N-type, there's gonna be a PN junctions over here, so high band of no connection, so these points are not going to be connected. So the point of this rambling is that it's going to be a very high resistance between these 2 points when this transistor is not turned on. And same can be said for the P-type. In this case, it's a channel of holes, or the lack of electrons, which is the majority carrier. And this is just a fun fact. This is why N-channel MOSFETs are more available and have better characteristics, at least in current and dissipation, because the electrons are way better conductor than holes, because their mobility is much greater, I think around 3 times. So this is why P-types are usually, they dissipate more power, they have higher resistances even when turned on, and same for NPN and PNP, but that's besides the point. So this is just a fun fact because I would like to show you the whole picture. So now that you know how this is working, here is much simpler. So this is the input portion, and as we discussed, if this is disabled or high impedance, then this should be high impedance when we want it to be as well. Well, here we have an input Schmidt trigger. This is just a fancy buffer that corrects the slow edges to make them sharp again. And it also has another feature. It can be turned on or off. If it's turned off, it's gonna go into the tri-state or the high impedance state. So this is practically not connected to here, so you can just remove it if you would to turn it off. And the other is going to the analog peripheral. So this is the ADC. That's gonna go to first the MUX and then to the ADC. So the analog ADC input is by default has to be a high impedance, so this is high impedance. If this is turned off, it's high impedance. If this is turned off, it's high impedance. So this is how we create the high impedance mode. But if we want to read the input, we turn this on, we turn this off, so all the input just goes through here and right into the registers. So this is how it works. You can just look at these tables. It has plenty of data around that. Different combinations of working. This is the different alternate modes that are connected to this pin. So each pin can be connected to different peripherals depending. So you should always check your datasheet. And it also has a few scenarios. So the floating pull up and pull down resistors. So if you're using input, so you can ignore everything else. We disable the output driver, so it's like an open switch. And the Schmidt trigger is turned on, so all the input goes through here. And there's another one for the output, so you can also have it turned on, so you can see the output state. So if the output is actually turned on, and you can use this peripheral as a push-pull or open drain, in this case to control the output, so either to pull it high, low, or just pull it low. And alternate function, yeah, this is how the input is dictated by the alternate function. And this is all that I want to show you from this. And later there are the registers, so there's not much over here left. So this is just the register, but now we're on HAL, so we don't bother with the register. If you want to do that, go back to my videos on the standard library where I describe how to read and make code with those. So let's just go to our project over here finally. So we start coding, so I'm gonna let a notation at the beginning for all those who don't want to listen to the theory. So let's start. I explained in many videos before how to create a blank project, and here I'm blank because, well, you might have a blank MCU or a blank board. So let's not create it in the default state, because I included it as a 407 debug board. It asked me if I want to initialize the peripherals, and I clicked no, and I reset all the pins. Only thing I did is I just set the clock input and the debug lines, and that's it. So for this case, let's go into another document that you should always have on hand, which is the schematic pack. If you go to your page for your processor, you have resources here, and you can click on schematics and download the schematic pack. And the schematic is useful to know how everything is connected. They also provide the user manual, but this is the more readable way for me because I'm used to schematics, and it's the fastest way. If we go to the bottom, here's the peripherals part. Here we can see the MEMS accelerometer, the buttons, and the LEDs. So apart from other ICs, which are like USB connectors and stuff like that, this is the other peripheral. This one is interesting. This is a reset button. So this is tied to the reset portion of the circuit. So the reset pin is the dedicated pin for reset. It has to be high, so it's enabled low. So if this pin is high, the pin is enabled, and the reset is if the reset pin is pulled low, then the processor is in reset mode, or the reset is high when it's low, if that makes sense. So in order to do that, this pin has to be always high. So it's gonna have a pull-up resistor, and it's usually external because the internal wouldn't work because the processor would not know how to configure it. So that's why we place an external one, but it says not fitted. So just not to make any confusion, let's go to the processor up here. Where is it? Here. And let's find the damn reset, which is over here. Okay, so this reset should be put to high. There's no resistor here, so that label is probably not correct. This 100K should be fitted in order for this processor to work. If you don't want to, if you want to reset it, you have to pull it low. So there's this button. So this button clicks, this pin goes low. So this button is reset enable high. High is the state of the button. So high is, let's say, closed. So when you close the button, the reset kicks in. So it's reset high, but the processor doesn't work that point. So you could call it the active low. So when you click it to the low part, it's disabled. So it goes to low when you have the button on 1. If that was confusing, this button is right the opposite, so you might draw a conclusion from that. Here we have this pin, which is just another user controlled pin, and it's connected to this jumper and this resistor, and through these resistors to ground. This is not fitted, and this button is not pressed, so it's not connected. So when nothing is pressed, everything is idle, this pin is connected to the ground, so it has a set state of ground. But when you click the button, the VDD, the 3.3 volt, gets connected to this point, and the whole voltage drop is over this resistor. So this pin, and because it doesn't draw much current, the whole voltage over here goes to the pin as well. So when you click the button, when the button goes into the state 1, the input goes to the state 1 again. So this is active high in this case, and this was active low because when you put the button close together, so the state 1, the input pin was actually going to the state 0. So this is active high and this is active low. Similar with LEDs. I'm not gonna pull out another sheet how the LEDs work, but basically this is a diode symbol, so it has a positive and a negative side. Current flows this way. So in order to turn on this LED, the voltage drop across it has to be positive and large enough from the threshold so the LED turns on and starts emitting light. We can see that the cathodes over here, which is the negative part, are connected to the ground potential, so this part has to be on a higher potential than this part. And in order to do that, this pin has to be high in order to enable this LED. These resistors over here just limit the amount of current going through the LED to not destroy them. Or destroy the pin, because you always have to make sure you don't destroy your processor, because if you destroy one pin, it's a crucial one and you cannot remap it because you have a PCB always done. then you have to throw it out and replace the processor. So this is really pain. So usually we would see for trivial things these resistors. That's why there's this resistor over here. It's 330 ohms, and if it's used as an input, no current's gonna flow through anyway, so this is like a short circuit basically, so it's not very usable. Why would you put it there? And this is simply for that if something happens, this pin is to this part, this pin is protected by at least 330 ohms. Okay, so this pin we said has to be high in order to turn the LED on. Great, so we know that these LEDs are controlled as active high. So to turn them high or emitting light, you have to put the control on high. Great, so now we know what we need to do. In order to test all of the three possibilities, the input, output and the analog or the tri-state some kind, let's control the LED, the button, and let's just assign a random pin to the analog value. So let's just choose one of the LEDs. They are on the port D12, 13, 14 and 15, and let's just choose orange. I like orange. It's not usually on the board, so PD13. Let's go to the PD13, it's over here. And when you click on it, you have multiple options. It's for the peripherals that are connected to this pin, so the analog peripherals inside and digital ones connected to the GPIO peripherals, in this case timers, and basically that's it. And the GPIO. GPIO can do input, output or analog. To drive the LED you have to source current, so GPIO output. So this is that. And then we need to define the button. The button is connected to the PA0. So this is the usually on the left bottom part. So let's click on it, and it has much more. It has all the ADCs, timers, USART, vents and stuff like that. But we need the input. So it's gonna choose the input. And then let's assign this pin right next to it as an analog in, and I have a multimeter over here, and I'm gonna measure the resistance from this pin to ground. It's not really the best way, but when it's turned on, this is the way we can measure it the most effectively. So we have initialized our pins. We told the software which we're gonna use, but we also have settings for them. We talked about them before. And we can do that by going to the GPIO portion, and here are all the pins. Let's just widen this up a bit. We don't need the processor right now anymore. And let's go to the PA0. So this is the software is gonna default their name to something to refer them in code. And if it's not changed by you, then it's not gonna be entered in the code. But to easier control the pins and wander around the code, when you have, let's say, all the pins initialized, you don't know which pins is what. If you have a motor control connected to the pin PC1, how do you know that? And the easier way to is to rename them. So if you go to the PA0, use a label, you can create your own label, and we're gonna see later in the code how that looks. So let's rename this for LED. You should do it more effectively. Let's say if you have, in this case, orange, you could do, if you have multiple LEDs, you can go LED orange. So let's do it in our case. And we also have two settings, the input mode and the pull up and pull down. This is the one that we chose, and the pull up and pull down are also here to choose, but we're not gonna do it because we don't want to influence the input, because we also have the outer part. And I'm probably just hazy. It's not the LED, it's the button. So in this case, we just write the button. So in this case, it's the button, and the LEDs are on the PD13. So LED orange. As we can see, for the output type, it has more configurations. First is the output level, which is the first output level that this pin is gonna be when it's gonna be initialized. So before all the code actually starts, when the initialization completes for the GPIO peripheral, what is the output state of this pin? And by default you usually use low, so 0, but there are certain cases that you might use high. So if you have an active low peripheral connected to this pin, so it's enabled when the pin is low, you actually want to have this pin high when it first boots up, because before the boot, before the initialization, the pin is floating, but then it's gonna need to be something low or high. So this is very important if you have something connected to it. In our case, it's an LED, so we want to have it turned off because it's an active high. So the turned off in the beginning. It's gonna be a push-pull. Here's also the open drain options that we talked about. Here are the pull resistors and the speed. So this is the speed that the output is gonna be able to work. So this is depending on the application of your choosing. For these LEDs, we're gonna choose the low. We don't need fast. And also the label, in our case, LED orange. The PA1 is the pin that we're gonna use for the analog. Let's just rename it for analog, just for the sake. It has the analog mode, and you cannot choose the resistors because that's the point of analog input, is to not mess with the analog signal coming out of the processor. So no pull resistor can be chosen. These are turned off. As you can see in here, in the sketch, these pins has also been renamed. So it's gonna be easier to refer to them in code. So in order to do that, let's save it. It's gonna make the folder structure, it's gonna do everything, and ding, it's fine. It's finalized, and let's go into our main. First thing, I just found it easier to be, just Control B, compile it, so you make sure that it works, no errors. So let's start. Let's find this initialization I was talking about. It's in the MX GPIO init. Here we can see it enables the clocks for all the GPIO. Here's the port A, port D, and H is probably for the clock. Here's the first defined output level, and we set it reset, and in this case this is 0. So we said that the LED should be low at the beginning. If we put high, here will be GPIO pin set. And here are all the settings for all the pins that we applied before. So this is where you would find them normally. So let's go to the main and let's do something. Let's see what we can do with GPIO. So let's go HAL, GPIO, control space, and let's see what functions do we have. Here are some interrupt functions, init functions, that's already taken care of. Lock pin, if you want to lock the configuration, so the one in the GPIO.c file that has been applied, if you call this function on the certain pin, it cannot be changed in the future until the processor is reset. The only ones that we really need is the read pin, which is going to read the output state, so that's that Smith trigger that we talked about before. Toggle pin, this is going to invert the state of the pin, so if it's 1 it's going to be low, and if it's low it's going to be 1. And the write pin is going to write the state of the pin, so if you put in an argument 0 it's going to pull it low, and if you put in argument 1 it's going to pull it high. So let's make something useful with it. The analog pin is already configured, we don't need to mess with that one. So let's create a simple example, inefficient, but it's gonna show you how the input and output works together at once. So while the analog pin is already configured and we don't need to do anything with it, let's create a simple code that's gonna toggle the LED if the button is pressed. So let's call a simple if function and call the HAL GPIO read input pin, and this is where the declaration is gonna get handy. So if you don't know where the button is placed, let's just call button, control space, and the GPIO port of the button. We don't care about what is the particular port and pin of the button. So this is where these macros really come in handy. So the code is actually readable for you, even if in a week you're gonna forget everything. So this is very useful. So if this function, which returns the GPIO pin state, which can be 1 or 0, if the button is pressed, this function is gonna return 1, and the argument of the if function is 1, so it's gonna go inside the if function. So let's toggle the pin. So again, LED orange, we don't care where it's turned on, we just want to initialize its port, and LED orange pin. So this is gonna toggle every time it goes in here. But with this processor is fast as lightning, so we won't be able to see, or the LED is gonna seem to be turned on all the time when we press the button, even for a fraction of a second. So let's just put some inefficient code again, HAL delay. Let's put, I guess, 100 milliseconds. So it's gonna be enough to click it, and if you're gonna hold it down, it's gonna toggle 10 times a second, which you'll still be able to see. So if the code works accordingly. So that's it. We're gonna save it, Control B to recompile, no problem. Let's start the debug session, go to your debug configurations, and go into the STM32 Cortex and create a new one. If you have compiled beforehand, you can see that it also recognizes this ELF file. This is the output file. In debugger, make sure everything is like this. There shouldn't be anything to choose. If you have multiple ST links, you should use this function. But in my case, for work and some kind of research as well, I use the J-Link debugger. So I have the onboard debugger chip, which is this one. So this chip that actually debugs the processor has J-Link firmware on it, and it's a legit tool from Sager. And that's why I'm gonna use the Sager J-Link, but you should always use the default settings over here. And it's gonna, everything else is gonna be the same, just a different interface protocol. So debug, and it's gonna compile again, save it, download the code and start at HAL init. So at the beginning of the main, and we can go step through the functions. And this is where the GPIO init function has already been called, so the pins are set. So I'm gonna grab my multimeter and measure the resistance from the PA1 to ground. So according to my multimeter, which doesn't read anything else than the over range, so the resistance to ground of that pin is too big for the multimeter to read, and I believe this is quite a good multimeter and can read over 20 mega ohms, so it really does what we thought it would do, so that's correct. The next part is, does it do this? So let's run this code, F8, so the code is running, no LEDs are turned on, and if I click the button fast, whoop, it turned on and off, turned on, oh, you have to be really fast. It turns on and off, and if I hold it, it just flashes rapidly, and so it flashes 5 times a second, because 10 times a second, in case we have a period of 100 milliseconds, so every 100 milliseconds it toggles it. So on and off, it's 200 milliseconds, so 5 times a second it turns the LED on and turns it off. So this is a simple demonstration how the GPIO peripheral works, and it's the most important because a lot of LEDs and turning on external parts is done this way, but the most important things and the really important stuff are also the peripherals inside behind the GPIO. So in the next videos we're gonna go through those peripherals one by one, maybe starting with my favorite SPI. But until then, have a good time, and if you have any questions, leave a comment or check my videos from before if you dare to go to the standard peripheral library. I promise it's a great learning experience, and at one point it really you have to understand everything that works, and the standard library is the way that you learn how the processor, and at least on the macroscopic scale, works, the peripherals and all that. So thank you for watching, and I'll see you in the next video.